Hello and welcome to another Tycho video. In this presentation, I'm going to be talking a little bit about 2023 BU. This is an object that a lot of folks are talking about primarily because it has passed by relatively close to Earth. I want to say at closest approach it was at 0.02 lunar distances, and that is below geostationary orbit. So it's pretty interesting from that perspective, but this is not entirely unprecedented because, of course, we have had impactors before. But nevertheless, a lot of folks are talking about it, and I have had a couple of questions about it. One of which was, how might you identify this object in a series of images? And could you use the known object module to facilitate that? And another thing I'll talk about here shortly is JPL Horizons. So JPL Horizons is a tool that I love to use for this kind of scenario, and then just go from there. So to go ahead and get started, the first question again was, how might you identify this object in a series of images? So here is the image viewer, and here is one exposure that has been captured of this object, and you may or may not be able to see it depending upon the video compression, but there is a very faint trailed object here. So again, this is the field of view, and then just right here there is a trailed object that's very faint. So before I zoom in on it, you can see that's the question, is this 2023 BU? So I zoom in a little bit here, and just basically according to the known motion of the object, it has a speed of 1440 arcseconds per minute, which equates to 24 arcseconds per second. And the exposure here is 20 seconds in duration. So you can compute the trail length, 20-second exposure times 24 arcseconds per second, and you get an expected trail length of 480 arcseconds. And so when I do the measuring tool here, the amount that I measured was 487 arcseconds. So that is what we expect. So this is very much likely to be the object. Now, the question I had here was from another user was, I have some images, but I do not see it listed in the known object module. So there is a module in Tycho that will overlay labels of expected object positions. So here's what that looks like. As you can see, we have different labels where it expects there to be certain objects, but notably absent is 2023 BU. So why is that the case? Well, for one, the known object module relies upon accurate orbital elements. So if you take a look at the MPC orbital database file, what it has for this particular object is quite different from what you would expect if you were to run those observations of this object through the FindOrb software. So the first line is the elements from MPC orbital database, and these are quite different from running those observations of the object through the FindOrb software. So there's a bit of a mismatch there, and that's one reason why that might not work if you are to use the elements from the MPC site. Now, again, they may have fixed that, they may have improved upon those elements. Again, it's just had a very short arc length, just a few nights, so there's some uncertainty there that obviously grows over time. But nevertheless, that is one explanation for that. So again, what I like to use for this kind of scenario, as I mentioned, is JPL Horizons. So let's go ahead and take a look and see what kind of result we can expect from that. Okay, so here are 4 exposures of this object. These were kindly provided to me by another Tycho user. As you can see, they are each 20 seconds in duration. So what I would like to go ahead and do now is go to Action, View Images, and this will present with the image viewer. Now as I zoom out a bit here, you can see this is the field of view that we are working with. And as I go to this corner over here, you may be able to just barely see it. So here is that trailed object. So at this point, what I would like to do is go to the JPL Horizons tool. So go to Ephemeris, attach from JPL Horizons, and what we have here, this is the target identifier. I went ahead and specified that earlier. So 2023 BU is the object of interest. And then we go ahead and do action or I should say ephemeris, attached to dataset. So once you do that, what it's essentially doing is informing the JPL Horizon service that here is the observer location and the date and time at which these images were acquired, and it will compute the object position, among a few other things. So as you can see, these columns have now been populated, and first and foremost, it does say that the object is expected to be in the field of view, so that's always a good thing. That means that we have actually acquired the object. And we also have the motion parameters, speed and position angle. So as I mentioned before on that second image, 1440 arc seconds per minute. And just to give some perspective, most main belt asteroids are moving at about 0.5 arc seconds per minute. So this is much, much faster than that. And it just gives some perspective as to this kind of object. So along with that, what I can go ahead and do here is I can define a couple of markers. So here's the starting point of the trail, create marker 1, and then what I'd like to do is go ahead and do the same for marker 2. So you just kind of visually inspect where you think the trail might end. So that might be marker 2. And then what I'm going to do next is then go to the midpoint. So we defined the trail, we can go to the midpoint here. And then from that, I would like to see how much deviation there is from that of the computed position. So I'm actually going to go ahead and do create marker 1 once more, and then I click on image number 2 again, and then create marker 2. So as you can see, the measured position versus the computed, we're only off by about, I want to say only off, but about 4 arc seconds. So normally that would actually be pretty horrific to be off by that amount, but due to the nature of this kind of object, that's actually a very nice positioning. Now, and part of it has to do with there are 3 key elements that go into computation of this object position. So the first of which is the I want to say the plate solution. So if you go to display catalog stars, you can see that the plate solution of the image is quite good. So all of the objects, the catalog stars and everything, they're overlaid where they should be. But so that's number 1, the plate solution. Number 2, and actually very, very important in this consideration of this kind of scenario, is the time stamping of the images. So when the images were acquired. So the date and time has to be extremely accurate. So if, for example, I were to go to the observatory setting and I wanted to say edit, and if I put in an offset, so if I were to offset the date and time of the images by just 1 second, what does that look like? So I'll go back to JPL Horizons and attach to dataset, and let's see now what kind of computed position that looks like. So now our image timestamp is off by 1 second. Well, now marker 2 is over here. So we went from 4 arc seconds of deviation now to 25 arc seconds of deviation, just by having the timestamp of the image be off by 1 second. So timestamping is very critical when you have an object with this kind of motion. Now the third one, of course, then is also the observer location. So what does that look like? Well, what I did here was, here's Google Earth, and I said, well, here's the original position, or I should say the actual position of the observatory that acquired the images, and I offset by 7 kilometers, or approximately 7 kilometers. So as you can see, just a small offset there, or at least small relative to what we're looking at here. And what does that look like? So I created another entry, and if I go to the observatory settings and say that modified by position, then what does that look like there? So go to JPL Horizons once more, and we're going to tell JPL Horizons that our position is different. Now I should also inform that the timestamp offset here has been disabled. So the only variable here is the position of the observer. So now I click once more, marker 2. So you can see now, again, originally we had an offset of 4 arc seconds. When we changed time by 1 second, we had 25. And now when we offset observer location by 7 kilometers approximately, now we have 49, approximately 50 arc seconds of offset. So these other 2 parameters, again, normally you're just concerned with the plate solution of the image, But these other two parameters, the timestamping of the images and the observer location, become very, very critical. So the tolerances are they have to be much higher. So anyway, that's this object. It's very interesting. And if you work on these kind of objects in the future, now you know to keep these other parameters in mind if you want to have accurate computation. So thank you for watching, and see you next time.